So again, good afternoon, everybody, and welcome to those who may be joining us during the recording. My name is Stephanie Lewis. I will be your moderator today. It is my pleasure to welcome our speakers today for transit prioritized vehicle scheduling at general conflict areas under connected and automated environment. Our speaker today will be Ms. Kiki Long. She is a research assistant at the Department of Civil and Environmental Engineering at the University of Wisconsin-Madison. She obtained her master's degree in traffic engineering in Shanghai, China in 2021, and she received her bachelor's of science degree also in traffic engineering in China. Her main research interests are connected and autonomous vehicles and artificial intelligence applications in transportation. So with that, Kiki, I'll hand it over to you. Kiki, you gotta make sure you unmute yourself.
Oh, yeah, sorry about that. Yeah,
And
thank
then
you,
let me
Stephanie.
let me bring up that presentation again.
Okay, I get the control.
Yep. Okay, go ahead.
My oh yeah, control. Okay, yeah, thank you. And today I represent the transit prioritized vehicle scheduling at general conflict area under connected and automated environments. So this is a program led by Professor Xiaopeng Li and Professor Chen Wen Li. So my presentation will cover this 3 years project. So in this project, we focus on the congestion problem, especially the subsequent delaying problem for the transit system. Thus, we proposed several methods to reduce the congestion and achieve the transit priority. And we will also introduce the CAV technology. We will explain why we believe the CAVs could help us be the solution to achieve the decongestion strategies. So my presentation will introduce the decongestion strategies at the 2 levels, at both the microscopy level, that is for the intersections or road segments, and also for the macroscopy level, that is for the road network of a whole city. So the first part, we will introduce how to measure the vehicles passing the conflict area more efficiently. And then we will talk about how to do the decongestion at the macroscopy level. We will talk about how to provide the speed guidance to the vehicles in the network to improve the city level efficiency. Okay, let's get started for the part 1. So for part 1, the microscopy level, when we talk about the traffic conflict areas. So this refers to the traffic conflict points, such as intersections, the merging roadways, and the work zones. So these locations present a common challenge, that is, we need to allocate time for vehicles from different approaches to safely pass the conflict point without collisions. We need to determine their sequence, who go first, who go next. So currently, from the perspective of traffic manager, these conflict areas suffers from the suboptimal scheduling strategies. Although we have some signal timing strategies that adapt to the real-time traffic conditions to improve the efficiency, the vehicles still need to yield or stop at the conflict areas. So this stop and go behavior causes both efficiency and safety issues. This is the limitation of our current transit priority system. So the emergence of the connected and autonomous vehicles, the CAVs. The CAVs provides an opportunity to achieve the non-stop traffic. In the future CAV system, CAVs share their information with each other and also the roadside units. Then like the roadside unit could collect the information of CAVs and then optimize to generate some optimal traffic management plans. And they could also get the optimize the trajectories for each CAV and then send these trajectories to the CAVs for them to follow. This will help us to achieve nonstop traffic, maybe as shown in this video in the future. But currently, we still believe that optimize the trajectories could help the CAVs to achieve more smooth and nonstop traffic. For the transit systems, we could also let the roadside units to collect the information of the bus or of the emergency vehicles, and then we could come up with some optimize the plan or signal timing system that give more priority to the transit vehicles. The current literature focus on two main strategies. So the decentralized and the centralized approaches. The decentralized approaches allows vehicles to independently schedule their routes, while the centralized methods, they relies on a system to coordinate all vehicles optimally. So this review highlights a gap in the current research. That is, there's no effective centralized optimization model for CAVs that address the coordination at conflict points with different time values and headways. So the time values means the time cost, like the cost of waiting time when they pass the intersection. For the transit, we think they will have higher time cost because there are maybe more passengers on the bus. And for the headways, that is maybe those large vehicles, they will have needs a larger headway to keep the safety. So this identifies a critical area for the future investigation. Here we try to describe the traffic problem as follows. That is, there is a conflict point with multiple approaches. Like within intersection, we may have 4 or more approaches. And all the vehicles are CAVs and follow the advised trajectory provided by a centralized controller. So our goal is to minimize the overall time cost of this system. We need to determine the order in which vehicle proceed. So the sequence of the vehicles will directly impact the system's time cost. Now, when we try to find the optimal vehicle scheduling solution, we need to consider the conflict area with multiple approaches, and we need to consider the different kinds of vehicles with different priorities, also called the value of time. And we need to consider the different headways for different kinds of vehicles. So to be more clear, here are some assumptions. This is at first, all the vehicles are CAVs, and overtaking is not allowed. We also assume that the CAVs are at the free flow speed when they pass the intersection, pass the conflict points. So here is the problem we need to solve. The described vehicle scheduling problem is usually formatted as a mixed integer linear programming. That is because in this formulation, there's a binary variable is assigned to each pair of vehicles, determine their sequence at the conflict area. That is, which vehicle go first and which one go next. And our goal is to minimize the total delay cost of all the vehicles. And this optimization problem have several constraints at here. At first, all the actual arrival time of the vehicles should be later than the earliest arrival time. The earliest arrival time is when we assume that the vehicles could go as fast as they can. That is when they accelerate to the maximum speed without the consideration of preceding vehicles or surrounding vehicles. And the second constraint is all the vehicles, they need to keep safety headway between other vehicles. That is, the following vehicles could not go further than its preceding vehicles, they need to keep a safety headway. And here are the definition of different kinds of headways. We need to notice that the number of those binary variables significantly impacts the solving speed of this problem. So the solution time grows exponentially as the number of vehicles increase. So imagine a busy intersection with thousands of vehicles. The current commercial solvers take several minutes to find a solution. That falls short of meeting the real-time requirements of traffic control, because for the real-time traffic control, we may need to make the decisions in a matter of seconds. So to address this problem with the constraints of limited time, we have developed 3 solutions. So at first, we could customize some algorithms to expedite the solving. So using the rules from the traffic system. Second, there are lots of heuristic methods in previous research. We could take advantage of these heuristic methods. The problem is those specific heuristic methods to one problem is hard to be applied in other problems. So we need to consider how to solve this. And the third group of solution is to reducing the problem size. That is, we could divide the vehicles into several groups and only deal with the sequence of these groups. We will talk about this method later. So at here, we could see we had 2 solutions, and the first solution will combine the first 2 features we mentioned. Okay, so for the first solution, it use a branch and a bound method. Here are several challenges we need to think about when using this branch and bound method. At first, we need to consider how to set up the branches to get different potential solutions, because the solution time also grows exponentially with the number of branches increase. And the second problem is how to set up the branches. The third problem is how to construct the lower bound and the upper bound for this algorithm. So unlike those traditional branch and bound methods, this method applies the characteristics of the traffic system to set up efficient bounds. The lower bound is given by the first in, first out solution, considering the homogeneous case. So in our report, we proved that the first in, first out solution considering a homogeneous case, that is with the minimum safety time headway and with the same value of time and without switching time. The solution of this simplified problem could be the lower bound of the original problem. That is, when we get to a bound that may have a solution lower than this value, we could just cut this bound. And then for the upper bound, it's given by a faster heuristic method. It will get a kind of okay solution really fast. And if we that is not the optimal solution, but if we find one bound with a solution may worse than these faster heuristic results, we could also cut this bound because the optimal solution could not be larger than the faster heuristic solution. That is how we use the upper bound and the lower bound to faster our solution process. And here are some details of the notation. Okay, so for the numerical results, at first, let's compare the number of explored nodes when we solve the problem. So given a certain number of CAVs, when we solve the problem of determining the passing sequence of these vehicles, we could compare our proposed method, that is branch and bound with valued cuts, with 2 baseline methods. The first one is the branch and bound method without value cuts. The second one is the Grovey. It's a commercial solver. It's widely applied in the industry. So we could see that the branch and bound with valued cut, they could reduce the number of export nodes during our solution. So the less nodes we explored in solution, the quicker we could solve this problem. And after compare the solving speed, we could then go further into the solution quality. That is, we compare the travel time delay cost of the of using different methods. We could see that our proposed branch and bound with value cost, this method could achieve the smallest travel time delay cost compared with other baseline models. That is, our solution quality is higher than the baseline models. So when we compare the computation time, we could see that the computation time of a proposed method is also smaller than the branch and bound method, a traditional branch and bound method without value cost and the Groby method. So after we introduce our solution algorithm, let's see how we could apply this algorithm in real intersection. For example, when we look into this intersection with two approaches, that is when the vehicles enters the entrance lane, we will optimize their trajectories, and the central controller will assign optimize the trajectory to each vehicle inside the entrance lane. So after the vehicle, those CAVs get their assigned trajectory, they will follow this trajectory until they pass the intersection. At the next time when the algorithm is activated, the new vehicles entering the entrance but without assigned trajectory will be considered in our next time optimization. That is their trajectory. They will get their new assigned trajectory. So this rolling time horizon will guarantee that all the vehicles will get their optimize the trajectory after they enter the entrance lane. So once they get the optimized trajectory, they will just follow it and pass the intersection. Then we compare the results of this proposed control with two benchmark controls. The benchmark controls including the adaptive signal control and the reservation-based control. We could see that the throughput of the proposed control is significantly higher than the reservation-based control. And the proposed model can also improve the total delay cost up to 80% compared with the reservation-based control. So this improvement is achieved by optimizing the departure sequence of the CAVs at the conflict points. So however, this method still have some trouble dealing with the heavy traffic. It costs over 5 seconds when the number of vehicles from 3 approaches exceeds 30. So let's make a brief conclusion for solution 1. That is, we proposed a new and efficient vehicle scheduling model, consider the transit priority. And we propose a branch and bound method that could be the Groby, and we could this proposed method could offer exact solutions. The final point is the individual-based vehicle scheduling that will result in less total delay and fuel consumption compared with the reservation-based vehicle scheduling. Okay, after we talk about the solution 1, let's talk about solution 2. That is, we use the platooning to group the vehicles together and thus reducing the problem size. So and here we how could we reduce the problem size by grouping vehicles in platoons? That is, all the vehicles in platoon could be regarded as one control unit. Then our algorithms is not to control the single vehicles. We are control the whole group of vehicles getting together. So the vehicle platooning refers to a closely following mechanism of vehicles in a coordinated way without having any mechanical linkage while maintaining a safety distance. So the platooning will help improve the effectiveness and the performance of the vehicles, and they will also help the vehicles keep a smaller headway and thus improve the capacity. Since all the vehicles they could be get together and get the information of each other, they will have less accidents. than without platooning. So after platooning, the resulting performance of vehicle scheduling is not yet to be investigated. That's our motivation for this part of the research. So when we talk about the transit priority in platooning, the first part is that we could use the platooning method to improve the efficiency of the whole intersection. Then the public transit could navigate more efficient through the traffic, ensuring its timely service and reliability. And we could also give higher priority to those transit involved platoons. Okay, here is the problem of vehicle platooning. That is, in here we could see those 12 vehicles. In previous research, the most common platooning method considered the platooning threshold. That is when the headway between two adjacent vehicles is smaller than this critical headway, they will be platooned. Here we can see if we use this strategy, those 12 vehicles are grouped into only 5 platoons. Then we only need to consider the passing sequence of these 5 platoons. So this decrease in the control units will significantly reduce the computation time. However, the platooning of vehicles may prevent us from finding the optimal solution. Since we define the optimal vehicle sequence that minimizes the total delay before platooning as the optimal solution. That is, without platooning, the best solution we could get. And we define the optimal sequence that minimizes the average vehicle delay after platooning as the platooned optimal solution. That is, when we set the vehicle platoon together and we only have 5 platoons, when we optimize the passing sequence of these five platoons, the best solution we could get. So since we have 2 kinds of solution here, the gap between the optimal solution and the platooned optimal solution is G. Okay, here's a detailed description of the solution gap G. That is the difference between the optimal solution and the platooned optimal solution. That is the optimal solution without the platoon and optimal solution after platoon. So our theoretical analysis try to find some features of G. So we found that the G is bounded. Its upper limit can be analytically solved. And we found that some cases should be avoided because in these cases, the upper limit of G is extremely large. Of course, we don't want to see this kind of situation. That means our optimal solution after platooning is far away from the true optimal solution. So based on this finding, we use a simple rule to guide the vehicle platooning. So besides analyzing the optimal gap, we also try to analyze how this platooning will efficiently decrease the number of control units. So in these 2 figures, we could see the expected number of control units decrease as the platoon threshold increase or the vehicle density increase. So combines the findings from previous analytical analysis, we propose a new platooning method. This method could be summarized in 3 criteria. We avoid the extremely large upper limit of gap and also avoid long accumulated headway. Okay, so let's go to the details of the criteria. The criterion 1 is we will platoon the vehicles when the 2 adjacent vehicles have a headway smaller than the threshold. This is a common way we do in previous platooning strategy. And the criterion 2 is we limited the cumulative headway of 1 platoon. And the criterion 3 is that the number of vehicles in 1 platoon should be smaller than a certain value. Okay, then we compared our proposed method to other two baseline methods in numerical experiments. The first one is NP. The NP is no platooning method. This is the baseline. The CHP is critical headway platooning. That is the widely applied platooning strategy that it only satisfies the criterion 1. And the proposed platooning methods will satisfy the criteria 1, 2, and 3. We first compare the solution efficiency. This figure plots the number of control units as the vehicle density increase. It's observed that both the PP, the proposed platooning, and CHP, the critical headway platooning, decrease the number of controlled units. So this reduction magnitude of CHP is even more significant than PP because PP is in proposal with more criteria. So this figure shows the solution time of this figure shows the solution time of when we use the Groby after we solve different kinds of problems. We could see that the proposed method, the proposed platooning method, the PP could keeps a solution time less than 0.2 seconds. Then we compare the solution quality. So compared with non-platooning, the optimal solution of CHP greatly increased with the vehicle density. The delay of proposed platooning is also greater than NP. That is, we already talked about this because we platoon the vehicle together, we will miss the optimal solution. But the increment of this proposed method is relatively marginal. That is, the proposed platooning method will lead to an average of 30% decrease, increase, 30% increase in the vehicle delay compared with non-platooning. While the CHP, they may lead to an average of 140% increase in delay compared with NP. So this demonstrates the advantage of the proposed platooning method because we could use the time less than 1 second to get a solution a little worse than the optimal solution. Here is a result when we combine the optimal solution, when we consider the solution time and optimal solution together. That is, we could see at here at 1 second on the left. That is, if we given the limited computational time to Groby, which kind of solution we could get using different kinds of methods. That is, we know the optimal solution may be 2.3, about 2.3, but that will take the Groby to for 1,000 seconds to get that optimal solution. But if we use the proposed platooning method, we may get kind of okay that is near the optimal solution just with 1 second. So that will help us in our real world practice. With this platooning method, we help the commercial solver get a new optimal solution in shorter time. So as a conclusion, for part 1, we introduced the 2 kinds of the solution to solve the problem of a general conflict area. The solution 1, it will provide a customized branch and bound method to help us solve the problem quicker than those commercial solvers. And the solution 2 is from the perspective of problem size. That is, we reduce the number of controlled units in our problem, help us to get a faster solving speed. Okay, that's all for the microscopic level. So for the part 2 of today's presentation, we will introduce the macroscopic decongestion strategy. That is the city level network decongestion under connected and automated environments. So when we talk about the macroscopic method, the first gap that is in macroscopic level is hard for us to apply those microscopic control. in city level. In city level, that is because we amidst the limited computational resources, we are not able to control the trajectory of each vehicle inside one city. So the second problem is those current traffic management strategies in macroscopic level, they are based on the macroscopic fundamental diagram, the MFD. So this MFD utilizes the perimeter control. This method involves applying the control strategies to the boundaries between different areas to regulate the flow of vehicles between areas. So this problem with the problem with this strategy may lead to vehicle queues forming at the boundaries. So to address these issues, we propose a control method from a macroscopic perspective. So at first, we introduce an area transmission model. So this area transmission model is inspired by the cell transmission model. It is suitable for the network applications. And this model does not consider the individual roads and intersections, but divides the city into various areas. Like this, in this figure, we cut the city of Madison into different districts or different areas. So we will achieve the control by calculating the parameters like flow density between these regions to decrease the travel delay and reduce the energy consumption. So this macroscopic approach will offer a new perspective and a potential solution to the existing traffic management strategies at the city level. So here are the two contributions of this work. At first, we propose an ATM model based on MFD. It's a decreased time and a decreased space framework capable of calculating the traffic flow in each area based on both current and historical area historical states. And we also proposed optimization-based optimal speed adversary strategy that use the constraints provided by the ATM model to fine-tune the CAV speed for minimizing the total traffic cost and fuel consumption in the city network. So here is the proposed optimal speed adversary method based on ATM. Here are the objective of this optimization-based method. That is, we try to reduce the total cost of delay and the energy consumption of all the areas and across the time. And here are two constraints provided by the ATM method. The first one is the constraints on traffic flow, and the second one is the constraints on density. There are also some other constraints, limited by the time. We may skip the details of the constraints and details of the constraints. We will list this method detailedly in our report on NICE's website. And so here is when we compare the proposed OSA method with a baseline that is without the optimal speed adversary method. We use the network of City of Madison. We could see that the proposed OSA method could reduce the energy consumption about 30%, and we could also reduce the travel delay of all the vehicles. We could also reduce the traffic clearance time. That is the time we need to wait after the congestion. So here are the two figures comparing the congestion measurements when we apply the OSA method and without apply the OSA method. We could see without the OSA method, the downtown area, the center parts, that is also where our university is located. It will suffer from the heavy congestion. But with the help of the optimal speed adversary, we could control the traffic flow to this downtown area and then reduce the overall congestion at the city level. Yeah, that's all for today's presentation, and I sincerely thank all the contributors of this research. All the members are come from the connected and autonomous transportation system, our CAS lab led by Professor Xiaopeng Li. That's all for the presentation, and thank you so much.
Great. Thank you so much, Kiki, for all the great information and providing us the information about your research. I would like to just quickly remind everybody how they can ask a questions. You have access to both the Q&A box and the chat window, which are provided at the top of your screen. It looks like we did receive a number of questions during the registration process. The first question comes in. It says, how is transit priority implemented in vehicle scheduling at intersections?
Oh, yeah, that's an important question. Thank you for mentioning that. Could I take control and go to previous slides?
Yes, absolutely.
Thank you. And yeah, so in the first solution, we actually set off the different priorities for the vehicles, and we set off different headways for the vehicles. So this is a general setting for the transit priority. So not only for the transit priority, but also for some emergency vehicles. For example, for the bus with a large amount of pedestrians, we could set up the priority considering the number of passengers in the bus. Yeah, and for the emergency vehicle, like the ambulance or some police vehicles, we could set up even higher priority for them. Then their value of time will be larger in our optimization problem, and they will be set with higher priority because our optimization problem will try to find the best solution which assign a smallest delay for those vehicles with highest priority, with highest value of time. That is how we use the weight of these delay costs to set up priority to different kinds of vehicles.
Great, thank you. There was another question that came in. It says, what is switching headway?
Switch. Yeah. On this page, yeah. There are two kinds of headway. The switching headway and the falling headway. The switching headway is when the two vehicles are coming from different approaches. Like for intersection, one vehicle goes from south to the north and another vehicle goes from the east to the west. So we think this kind of switching headway should be larger than the following headway. The following headway is when the two vehicles are coming from the same entrance or same approach. That is, they only need to keep falling headway as the minimum falling headway is like the safety falling headway when they drive on the same roads. The switching headway is usually a little bit larger than the falling headway. Thank you.
Great, thank you. Are vehicles platooned in your research?
The platooning method. Yeah, thank you for this.
Sorry,
question.
how? I apologize. I read that one wrong. It says, how are vehicles platooned in your research?
Yeah, that's an important question. At here we could see go to this page. So at first we talk about the traditional way of platooning vehicles together. That is when the headway between two vehicles is smaller than a certain threshold, there will be platoon. For example, if these two vehicles, their headway is smaller than a threshold of 2 seconds, then they will be grouped together. And then after our theoretical analysis, we add two criterions to our platooning strategy. That is like shown in these algorithms table. That is, we first check if their headway are smaller than a threshold, and then we check if their accumulated headway is smaller than a threshold. If not, we will reduce the number of vehicles inside that platoon until these two requirements are met. And after that, we will check the third criteria, that is whether the whole platoon could satisfy the requirements of number of vehicles. So after the criteria, all the three criteria are satisfied, we could platoon the vehicles together. That is our proposed platooning method.
Great, thank you. It looks like we have one more question. It says, how is your platooning method and current CACC and ACC methods? Or what is your platooning method and current CACC and ACC methods?
Yes, thank you for the question. So actually, this platooning method is from the perspective of vehicle scheduling. So we try to analyze how to platoon the vehicles together. And then for the mentioned CACC and ACC methods, they are vehicle control strategies in platooning. That is, after we know these two vehicles need to be platooned together, we could apply the CACC or ACC methods to control the vehicles to achieve this kind of platooning. That is to help the vehicles they driving a smaller headway and share their information. So our research is from the perspective of vehicle scheduling. That is, before we make the decision of platooning vehicle together, we need to decide why these vehicles need to be platooned and what's the vehicles need to be platooned together. Should they be form a one platoon, or should they be cut into two platoons? Yeah, so we try to find out some theoretical results about this platooning in efficiency. So based on our results, we gave with some platooning strategy, and based on this, then after we know these three vehicles need to be platooned together, we could use those widely applied CACC or ACC methods to achieve that platooning in vehicle control level.
Great, thank you so much. It doesn't look like we have any questions left. I did place in the chat window as well as on the screen. Well, you may want to use the one in the chat window. There is a link for today's evaluation. Please take a few moments to complete that evaluation, as the feedback is very important to the NYSER webcast series as well as to our presenter today. So Kiki, thank you so much for sharing your research. Please stay connected to the NYSER website for all of our upcoming webinars, as well as you may check all of our previously recorded websites. So on behalf of the National Institute for Congestion Reduction, thank you so much for joining us today, and we'll see you all next time. Bye, everybody.
Thank you.